thank you very much for giving me this opportunity to tell you a bit more information about some of the activities we are performing here at PSI related to these two SCCRs, one which we were talking about today, the storage SCCR, but we also are home, or PSI is home also to the other SCCR BioSuite, and with this platform, which we call the Energy System Integration Platform, we actually provide a research and technology transfer platform for both of these. Why we call it Energy System Integration, better now, is because we want to demonstrate technologies on this platform which combine, which link the electricity system and the natural gas system, and we will perform crossovers, operation modes, which combine these two networks in order to flexibly provide services then to both grids, to both networks, and also in terms of making best use, as we heard already multiple times today, of any renewable electricity which is being produced. Because we are also serving the SCCR BioSuite, we also consider biomass resources as a feedstock into these system arrangements. You can also show what we intend to realize, or what we are currently in the process of realizing in the way you see it here. You have the electricity network on the left and on the right, and this requires positive and negative load in order to balance demand and supply. And the platform, the linking technologies are the components you see in the center of the graph, where there is also then gas networks for hydrogen and methane in that case. Another rendering of the activities is shown here. This one actually sort of outlines the different lines of activities. We want to deal with what we call dry biomass. This is more or less wood in most cases, which we treat via gasification, even though gasification is not a research topic we are intensively involved. We actually just use whatever is available as technology, but then treat this synthesis gas appropriately, such that we can feed it into a methanation step. And this is, in this specific case, an in-house proprietary technology of PSI. We can also process, or we intend to study technologies and processes dealing with wet biomass. This is everything which contains considerable amounts of water, let's say at least 50% by weight. And we will treat this type of feedstock then in a different way via hydrothermal methanation and in supercritical water, in order to also produce methane, which can then finally be fed into the network. Another source to be used and which is being studied is other CO2 sources from industrial processes, or actually even from air. So there is the link again to this company Climeworks, which was mentioned already before. We will likely have a certain module extracting CO2 from the air, which we can then simulate in order to, or use to process in our methanation step, as it is shown here. Another attractive source, even though I was a bit astonished by the results shown right now, which showed CO2 from cement plants not to be, at least it looked to me like a preferred source cost-wise, but that was probably mainly due to the assumption which was the electricity supply. What we want to deal with also is CO2 from cement plants. We want to study these kind of processes because there is a real big local point source of CO2. So if we would be talking about real megawatt size power to gas units, methanation units, this would be the place to be and the CO2 to take from. A further line of activity are then the ones which are more closely related to what we have been discussing today in terms of all the electrochemical applications, and specifically the ones where electrolysis is being involved. What will be studied on the platform is that we take profiles from a photovoltaic array, which is installed, for example, here on the west side of our premises. We will feed these profiles into the electrolyzer in a sense that we try to run it according to these profiles and see how we can actually cope on an integrated system aspects with these dynamic behaviors. The re-electrification would be done by a fuel cell, and actually both technologies for the electrolyzer as well as for the fuel cell would be PEM-based, because that's the technology we feel most competent about here at PSI. The hydrogen would then be again used in the methanation reactor we also run here at PSI. Finally, there are two overarching lines of activities. Catalytically supported processes is an issue, is a topic where a lot of groups within the General Energy Department here at PSI are being active with. So we also do further research into providing more advanced, improved catalysts for the various technologies which require these. And we even want to go into issues about synthesizing such catalysts then in the maybe kilogram range. Another overarching activity would be diagnostic issues. As we are a research institute, we like to really drill deep into all these kind of processes and really want to understand them to the very detail. And having the proper diagnostic tools for this is an absolute need for this. And we are furthering developing certain measurement technologies in order to get better here. Last not least, energy scenarios, technology assessments like we have seen in the previous talks will be also applied within this realm, within this topic of the energy system integration platform. This summarizes what I just said in terms of the subsystems to be realized. We'll run this dry biomass to SNG pathway, wet biomass not only to synthetic natural gas, but maybe on the mid and longer term perspective also to synthetic fuels and other valuable chemicals. Then the industrial CO2 reuse is a point we will study, sort of conventional power to gas, but then more with an emphasis on hydrogen and maybe its use in mobility applications, as well as power to power questions and tasks. Plus these cross-cutting activities on catalysis, process diagnostics, and energy system analysis. This is how it should finally look out, or how it will look like, and how the layout is foreseen. It will be placed on the eastern part of PSI, close to our other experimental facilities. For example, the methanation unit will be actually inside in one of our experimental halls, and all the rest then the platform just outside, and all the individual components will be containerized, like for example the electrolysis unit here with its gas cleaning system plus the fuel cell as located here. Containerized because we will start off within this current first phase with a certain selection of technologies and components which we deliberately have chosen. But we would like, of course, then to either introduce second generation type of units then at a later stage, or also be open for any industrial partners or other partners who would like actually to use this platform as a testing and qualification purpose. This is a model of it, as it hopefully will look like pretty soon. The ground is prepared currently. The metal structure, the platform itself, should be set up within the next 3 months, and then we will successively install the individual subsystems on it, and hopefully we'll be able to generate first data by the end of this year. This AZ, Energy System Integration Platform, is actually also an element of the Park Innovare concept, which is mentioned here. So PSI has been selected as a hub, as a satellite hub actually within the Swiss Innovation Park initiative, and this platform and maybe a successor of it at an even larger scale, which might not necessarily be located at PSI, is part of the concepts of the ideas which are developed within this Park Innovare. The operation modes we envision to realize and to operate and to actually qualify the hardware for is this synthetic natural gas production from wood, as well as the SNG from wet biomass. We will also compare this then with with methane synthesis from other sources, like the industrial CO2 from, for example, a cement plant. We will study the power to gas for the hydrogen route, and also power to power issues, combining then electrolysis and the fuel cell re-electrification. We want to do this as individual components to see their behavior more clearly, but of course also in some highly integrated and specifically also dynamic type of operations, like for example this what we called it here, dynamic power to gas, which should even operate without a significant, at least, intermediate gas storage, in order to see whether all the system components would really be able to act together in a somewhat optimum way without the need for significant storage capacities. And last not least, frequency control issues, very highly dynamic requests for specifically the electrolyzer and the fuel system in order to provide grid support, grid services for stabilizing the network if needed. A few more details on two of these operating concepts. Power to power would make use of the components down here. electrolysis, storage of hydrogen and oxygen, and then re-electrification via the fuel cell. And this is how it would be then connected on the platform itself. This is the hydrogen and oxygen production operation mode. We take this profile from the, or we take electricity from the grid based on a profile which either a customer provides to us, like for example Swissgrid, who is interested in knowing how well such technologies could provide respective services to the grid. We run the electrolyzer according to this profile and have then hydrogen and oxygen temporarily stored in our tanks. And at a different time, at a later time, we would do then a similar thing, operating the fuel cell according to a certain dynamic behavior, according to a certain profile required or asked for by the electricity grid. Power to gas would be realized such that, for one thing, we simulate certain gas compositions as they come out of biomass gasifiers, for example, or that we simulate certain CO2 mixtures with other components as they are likely to become available from industrial processes. We add hydrogen from our storage system and run then this methanation plant in order to validate the efficiency, so the conversion efficiency of that technology, and or also to show the dynamic behavior, how fast we can ramp up and down such kind of a unit. The fully integrated mode would look then like this, for example. We again take the fluctuating electricity from the grid, run it through the electrolyzer, produce hydrogen, clean it, and then if we want to avoid the temporary storage, run it directly into the methanation unit and provide, for example, equivalent amounts of CO2 to then convert it to synthetic natural gas. So far so good. A few more details on these two specific lines of operation. First one, the pathway which includes the electrolyzer and the fuel cell. This is again that subsystem outlined a bit more in detail. Originally we were, and we are still actually thinking about it, but we will not realize it, having also a hydrogen refueling station. This might come in a next phase. What we will focus on now is on this path and on these components. As already described, take data from a PV array and use it in order to operate the electrolyzer, which will be based on PEM technology, which would also or will also allow to operate it at elevated pressure. This actually saves then on the compression cost. We can directly then feed the produced hydrogen and oxygen after doing some cleaning, and cleaning means also drying and dehumidification, can directly feed it then into our storage tanks without any further investment of mechanical work, which could then be reused in times where it's needed and where it makes sense for re-electrification with hopefully this efficiency of 60 to 70%. I forgot to mention that all the components on the platform are being designed or chosen such that we approximately meet a 100 kilowatt scale, because we think that if we have all the information then available on this scale, it should only be one step further to scale it up to a megawatt size system, which should be then actually somewhat commercially viable. It will be commercially, or certain components will be commercially available systems like the electrolyzer. This has been bought. Also the gas cleaning system, as well as the tanks, where we have our own proprietary technology included, is in the PEM fuel cell stacks. Finally, the pathway on the methanation side. I mentioned already that we will, or our technology, even though it was specifically developed and designed originally to use these kind of mixtures from biomass feedstocks, we will run it on different CO2 or carbon sources, which means different mixtures of CO, CO2, and other gases needed, and we will prove that it will work for all of these different sources. We have here, and the different sources actually allow for then studying cases which relate to different power-to-gas applications depending on the scale we are talking about, and thus also on the level where we, for example, take the electricity surplus from the respective electric grid, and also dependent on the amount of CO2 which is locally available. If we talk about using CO2 taken from the air, we are rather talking smaller scales. Biomass-based systems might be maximum megawatt scale, whereas for these large local point sources like a cement plant, we can even dream of going larger. This will allow us then to reuse significant amounts of hydrogen, and thus electricity it has been produced from, and produce SNG, which will be fed then back into the natural gas grid, into the pipeline system. The technology we do this, and which we have developed here over quite a couple of years at PSI, is based on a fluidized bed technology. It has certain advantages of the conventionally applied methanation reactor type, which is based on fixed bed systems, which require, because of the exothermicity of the system, to do it in stages, in multiple reactors with cooling in between. We have a fluidized bed reactor with cooling loops inserted. Thus we can actually, where the heat is actually produced, we can extract it, and thus have a very nice local temperature control in order to run the reaction exactly at its optimum conditions. This is rendering of the system as it should be put up within hopefully a short time. We now expect it to be delivered in somewhat end of June this year. It will be a pressurized system, so this is actually a first off. All the previous tests of this fluidized bed technology have been on close to ambient pressure. It will be heavily equipped with measurement and sample extraction possibilities, such that we can really study it in very detail. I think I'll actually this is the last slide. The questions to be answered are first, can we really take all these different CO2 sources and what kind of capacities and dynamic profiles are really required, and what is sort of the envisioned optimum power rating of such a technology. That's it. Thank you very much for your attention.